All right, I'm showing 9 o'clock, so we're going to go ahead and get started. My name is Mike D. Lecluse, President of Lesman Instrument Company, and I'd like to thank all of you for taking time out of your busy schedules to join us for Best Practices for Process Protection and Safety Shutdown. Today's webinar, we're going to discuss how industry security demands are leading to advances in process control instrumentation, some common problems customers encounter using traditional switches, whether they be pressure or temperature, some common applications for process and instrument protection, including alarms, interlocks, and critical shutdown systems, and we'll discuss some recommendations for effective protection and shutdown instrumentation. Our presenter today is Bruce Albert from United Electric Controls. Bruce has worked in the process control instrumentation industry for nearly 20 years, the last 15 with United Electric Controls, where he served as a regional manager and now as North American Director of Sales. He's been a member of ISA and LinkedIn's ISA 61508 Functional Safety Group. Bruce is also certified for the implementation of Emerson's Delta V control system. The phone lines will be muted. There is a question tool built into GoToWebinar. If you just type your question in, we'll make sure that we get it answered. With that, I'm going to turn it over to Bruce.
Thank you very much, Mike. And I too appreciate everybody taking time out of their schedule to attend this. Hopefully you'll find it valuable. As Mike said, we're going to look at the advancement in the field of process protection, protecting people and equipment. And we're going to look at the three main areas of process protection: alarms, interlocks and permissives, and shutdown systems. And we're going to see if we can leverage the advancement of technology to help achieve a greater level of protection. So let's dive right in and see what we find. There's been a lot of improvement in the area of process control. And I refer to process control as, well, the control of the process that creates a product. Everything that goes into making, for example, a can of Coke, a number 2 pencil, an aspirin, whatever it be, process control optimizes operations within the limits. These limits are what we're going to explore, but let's continue here for a second. Technology has brought a huge increase in availability, reliability, and accuracy in process control. We now have very smart instruments, incredible valve positioners, increased computing power and flexibility in PLCs and DCSs. In some cases, these things can even talk to themselves, sensor to valve, sensor to sensor, to accomplish what's referred to as control in the field. An ARC paper from 2009, which technologically speaking is ancient, found an 80% increase in the mean time between failure compared to traditional DCS by using control in the field. There's been an amazing advancement to make sure that that Coke, that pencil, that aspirin is rolling off the line constantly, consistently, and with the least waste possible. But there is another area in your process, and we're going to see, has this incredible technological edge translated over to this area of the plant? It's easy to focus on the process and process control, as it's essentially your cash register. The product is what makes you money. But there is another part of that process, those limits I mentioned. Process protection and safety shutdown is what I'll call it for the sake of today. And there's basically three areas in protection if you really boil it down. You've got alarms, you've got interlocks and permissives, and if all else fails, you've got your shutdown system. advancement here has been somewhat limited, and there's a few reasons for this. One I mentioned, the cash register and the focus on process control. But there's also the appearance or thought that protection systems are separate. It's peripheral. It's over there, not what you're concentrating on. Sometimes it actually is separate, like in the case of safety systems, where it's required to be separate. Speed is critical in this arena. If something goes off the rails, literally or figuratively, speed in responding to protect your assets is crucial. The increased computing power of the field elements that we were just talking about on the process side leads to longer response times, which can be a negative when you're trying to protect something where speed is critical. It's good for control, it's bad for protection. The function of alarms, interlocks, and shutdowns are discrete. They're on and off. This is another area where there isn't as much to communicate, capture, analyze, whatever. So all those features of process control, there's nothing for it to communicate, capture, analyze. Then there's maybe the biggest one of all, the existing architecture, the existing control scheme that you have, or that a process has that calls for a discrete device to do the discrete function, been designed that way. The advancement in the area of protection has really been, up to this point, using those super smart process instruments in the protection systems, shoehorning them in, if you will. And we're going to take a look at that and see if that is really advancement. So let's take a look at these three areas and see what the demands are and if we could improve the performance of our process protection. First up are alarms. A critical attribute for alarms is speed. Limits known, know what you can operate at. So the faster the response, the faster the reaction. That same ARC paper from 2009 found the most significant improvement in systems was the reduction of response time. That control in the field reduced response time, and that's where they saw their greatest gains. Another attribute, which is opposed to the first one, is finding that alarms can happen too often or too quickly in some applications. So you've got some applications that need it fast. You've got others that can result in an alarm blizzard, is what I'll call it. And if you've ever been at an operator station when something goes amiss, the alarm windows pop up so quickly, and there's so many, it completely covers the graphics, the HMI graphics showing, and you lose visibility on what's going on. It's an avalanche or a blizzard. So a truly advanced device would need to have the ability to do both, to react fast enough to meet the need of one area and have the ability to differentiate between a real or a transient condition for another. In addition, it should be flexible enough to match the existing architecture, because you don't want to redo the whole thing, and match the control scheme. As always, it should be non-proprietary, leaving the choice up to the customer, allowing it to work for anyone, anywhere. So let's Let's take a look and see the ways alarms have historically been handled. First off, you've got, let's use a mechanical switch doing the sensing. Discrete device matching the discrete logic required. It's either within or outside the limits. So here it's connected to a logic solver, a PLC. Back in the day, mechanical switches were hardwired, and some of those still even exist today, but they're pretty few and far between. So there's a match between instrument and logic, but switch is not the most technologically advanced nor reliable instrument here. So what have we moved to over time? There's a double pole switch where one signal goes to the logic solver and the other is hardwired, sort of a redundancy, hedging of bets, if you will. This is the quote unquote advancement in alarming. Not sure about that. So let's take a look somewhere else and see what we can move on to. The process transmitter. All those terrific features of the process control instruments are they're just too good to pass up. We want to put them in here. We'll shoehorn it in. Sure, it's not a discrete device. It takes some time to process. It's pretty slow, and it doesn't match the existing architecture. But like the old Midas commercial used to say, guys with the big hammers will make it fit. There is another option, a hybrid device, one that can either be an electronic drop-in replacement for a mechanical switch, requiring no external power, but having all the functionality of a smart process control instrument. So getting all those features that matches the existing architecture, or it can be a transmitter switch combination, allowing for it to fit whatever functionality you're looking for. This hybrid device, ideally, it would have an extremely fast response time that could fit the fastest requirement, but should also have the programmability to allow it to determine if it's a real or transient condition to avoid that alarm blizzard or alarm avalanche. Put intelligence in the device in order to do that. That would be the grail on alarms. Next up, interlocks and permissives. These are a little different from alarms. First, they're not as speed dependent. Reliability is key here because it is a go, no-go gate, if you will, for the advancement of the process. Like a downhill skier going through the gates, you have to hit a condition before you can go on to the next thing. Devices here need to correctly identify the current condition and be operational and accurate in reporting that state. So here, we really need the highest of reliability. We need it to be repeatable, to recognize that state over and over and over again. The ability to recognize between a real and transient condition is still good. Diagnostics are really a must to help out with the reliability. We need to know if it's alive and healthy. And the final two, of course, non-proprietary and flexible enough to match the existing architecture. So how do these look over time? Well, again, in the past, mechanical switches. and they're still being used. They're still doing their job. In this case, it is connected to the PLC or the DCS, excuse me, as it's an integral part of the process. It's a gate. It's a condition that needs to be met to move on. So here's cutting edge circa 1962. Next up is the process transmitter. Again, features just way too tempting to pass up. Here, it's not as bad a fit as alarms, but it's still a little out of its element, still doing the discrete function, maybe or maybe not a fit into the existing scheme. Probably not, because a discrete function is designed around a discrete device. It's still certainly slow, but that isn't as critical here. The process transmitter is very, very reliable, and that is what we are looking for. So could there be something that would solve all of this? The third choice, or the third device that we're seeking here, would be an electronic switch. Something doing a discrete function with that reliability of the advanced electronics. So a combination of the intelligence and reliability of the transmitter, but fitting the architecture that exists or the discrete function that will always be there. Again, a discrete device doing a discrete function will always do better than a analog device attempting to do the discrete function. And we'll see that in our next area, which is emergency shutdown systems, or ESDs. These can require extremely fast response times. Think gas turbines spinning at upteen thousands of RPM. You're going to need to react quickly in order to catch anything before something bad happens. It is absolutely critical to correctly identify the condition. In this case, because you're the last line of defense, you're shutting down the whole process. You're tripping it. False trips, spurious trips on an ESD are completely and totally unacceptable. Excuse me. It has to be reliable. Again, see above. If you're going to shut something down, it has to be reliable. It can't have a false, can't be Chicken Little. Can't scream the sky is falling. It has to be reliable. Because of this, employing ESD devices have been put together in redundant packages, voting logic packages. They use redundancy and divergent technologies. Different device, not only manufacturer, but different operation of device to avoid single point failures. With all this, there's also a move to minimize complexity. The more complex, the higher likelihood of failure. If you have 3 devices out there, it's intuitively obvious that you have 3 times the stuff that could fail. So in some cases, like safety instrumented systems, you have redundant and divergent technologies, both. And speaking of safety instrumented systems, there's also specialized certification that can be required. So we've got we've got a whole mouthful here of needs on ESD systems, and that's appropriate because this is the very last line. So for ESDs, the devices need to be extremely fast. They need to have the highest of reliability. They need to recognize real versus transient because you're tripping the whole plant. They need to be able to report their health because they need to be up and vigilant. They should be, and now, I mean, this list goes on and on. We're pushing our luck, yeah? They should be cost effective to allow for implementing redundancy in voting logic. And if needed, they should have that required certification. Of course, non-proprietary and flexible enough here, in this case, to match not only the legacy system that's in place now, not even the current system that you're looking to achieve, but even future needs. With the focus on safety, there's a lot of regulations and they always seem to be changing. So to have something that can provide some flexibility to match whatever you could imagine on the horizon would be good. So let's take a look and see what a traditional approach to a shutdown or ESD system looks like. Here's the traditional approach. There are a lot of components, as you would imagine. Again, they're very complex. So this complexity leads to a greater likelihood of failure. Too many things, too many places to go awry. But this is the traditional approach with the process transmitter feeding a trip amp onto a DCS or PLC, and that coming back to a safety relay and onto the valve. Each one of these things is doing a job, doing its job very well with the highest of reliability and everything. There's just too much there. So a more advanced approach or a new approach would be something like a hybrid device again. Still feeding that DCS, but having the instrument itself and the DCS capable of communicating directly to that relay. Kind of built-in voting logic, if you would, and on from there to the valve. So an elimination of the trip amplifier completely and a lot of the associated wiring and communication can be greatly simplified, and a true technological improvement rather than the shoehorning of the technology that we recognize as being nice into an application that it's really not made for. So in conclusion here, the technology advancements that's increased productivity and reliability of process control hasn't had the same impact on process protection. What little has been achieved has been by, frankly, misapplying those advanced process instruments into the field of protection. It looks good, it sounds good, but when you look at what it's doing, it's a misapplication. The right device built for this area of protection and safety could have just as large an effect in the area of safety as the process control instruments have had on the process side. To avoid that dreaded shoehorn issue, the right device really should meet all of the requirements. If it only has some, then you run into that problem of making something fit because it's the best you have rather than everything you want. It's time to bring the advancement, technological advancement to the protection side, the protection of people, processes, and property. So the takeaway, the recommendation here would be to seek out a device, an instrument, meeting all the requirements that we've gone through here: fast, reliable, intelligent, can think. It's actually got intelligence in the device, just like the process control ones. It can recognize a transient versus a real condition. Diagnostic, flexible. It should be a true drop-in replacement for old discrete mechanical switches without any wiring or control scheme changes, and or depending on your current control scheme, a transmitter switch hybrid. But no matter what it is, it has to be what you want it to do. It should be also certified, repeatable, cost-effective, and of course, non-proprietary. So that is what I have for today, and I would like to open it up to questions that you may have on today's presentation.
Bruce, thank you very much. I don't have any questions that have come in yet at this point, so we'll start to wrap it up and hope that some questions do come in as we proceed. I'm going to take over the presentation here real quick, Bruce.
Sure.
And I got something in the way here. Can you see my screen now?
I can, yes.
Okay, there we go. So we'll continue to wrap it up here, and I'll see if any questions come in. Bruce, again, thank you very much for your presentation. If there are any specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you do not know your account manager, feel free to ask for me, Mike DeLacluse, and I'll make sure that you get taken care of. You can also reach me at miked@lesman.com. If you want to know more about the technologies we supply, please follow us on social media. Dan's blog is very active and has tons of great tips. All of our webinars are posted both on our website and on our Lesman Instrument Co. YouTube channel. If there are some topics that you'd like to see us cover in future webinars, please feel free to send me an email with the subject. We have access to lots of product and process specialists, so if there is anything you'd like to know more about, please email me at miked@lesman.com. Our next webinar, I think I've got a slide here. Our next webinar will be on May 24th at 9 a.m. The topic is Transmitter Selection and Specification Made Easy, and will be presented by Chris Kepper from Honeywell. Honeywell has developed some very interesting configurators that can help aid in the selection and shows you pictures, drawings, and all sorts of things as you start to build up a specific transmitter. We do have a question that has just come in. Let's see, do the hybrid devices include instruments that are analog with switches, or Namur type devices that have, he says 8 to 16 milliamp current signals to reflect the status, but I think it can do more than that. Bruce, can you expand on that?
Yes, I could. Either one of those would fit the definition of a hybrid device because it's doing its, let's just simplify it and say it's doing its main reporting as a transmitter, and then it's got either, as the question came in, a switch output or a status output on the other side. So it's sort of redundancy in a box. The milliamp signal, if I understand the question correctly, that's reporting the status, can be used as another output, if you would, making the device a two-output hybrid type device. Hopefully that answers the question.
Hopefully. If not, I do know this contact, so we can get back to him and make sure that we have it clarified offline. If there are any other questions, we've got another minute or so before we wrap up. Again, feel free to email me directly at miked@lesman.com, and we'll make sure that you get it answered. There are not any other questions coming in, so we can probably conclude this webinar. Again, Bruce, thank you very much.
Thank you, Mike.
And we'll go ahead and conclude.